This is our POGIL-5B activity, pre-POGIL-5B, and we're going to focus on drawing cyclohexane chair conformations. So we just did Newman projections for a straight chain, just a butane. This is cyclohexane. So this is cyclohexane. You've probably drawn it like this. And we're going to talk about how to draw the chair conformation. And your learning objectives will be to draw these lowest energy chair conformations. And you'll need to be able to label the axial and equatorial positions. And we'll also do a ring flip. So let's talk about how to draw the chair conformations first. So the best way to do this is to imagine your paper like this, kind of like what you did in elementary school. And then you're going to draw one carbon to that carbon, and this carbon goes to the line, this carbon goes to the line, this carbon goes there, this carbon goes here, and this carbon goes here. And what you'll see is these here are parallel, these here are parallel, and then these here are parallel. Okay? So that's the first thing you do. So you draw your chair. Now, the second thing you do is you draw in all axial hydrogens. And you can always go back and change the hydrogens to carbons. These will be perpendicular, so in the plane, they'll be alternating up and down. And that's the second thing you do. So I just come here, I go straight up and down the plane. That's up because that point goes up. Okay, so that's going to be axial up. And then the next one points down. This is going to be axial down. This is axial up, axial down, axial up, axial down. Okay, so they're alternating up and down. And then the third thing you want to do is draw in all your equatorial hydrogens. So your equatorial hydrogens will be, if this is up, then this is equatorial down. So once this is down, this will be equatorial up. And it's also alternating. So this is axial up, this is equatorial down. Do not draw those hydrogens inside the ring on your equatorial. This is axial down, this is equatorial up, equatorial down, axial down, equatorial up. You see how I draw that outside the ring for my equatorial. So these are my equatorial. So you need to be able to draw your chair conformation and label your axial and equatorial either up or down. Now, let's try to draw some disubstituted cyclohexanes. So here's some compounds we'll focus on here. So here's this one. Here's this one. Now, your goal is to draw the lowest energy chair conformation and label axial and equatorial. So here we have, let's go ahead and name this. This is 1,5,6,1,4-dimethyl cyclohexane. Now, is that correct? Well, we have to do cis and trans, just like we do with double bonds. So these methyls are both above the ring. They're coming at you. So this is a cis 1,4-dimethyl cyclohexane. So we draw our chair. You can draw your thing here. And so we're going to draw our chair. Okay, so there's our chair. And then the second thing we do is we draw all our axial. So axial up, axial down, axial up, axial down, axial up, axial down. And then we're going to draw in our equatorial. Equatorial down, equatorial up, equatorial down, equatorial up, equatorial down, equatorial up. Now, what we can do is then we can put in our methyls. So if we want to make this our 1, and we want lowest energy, so let's just go ahead and put this CH3 here. So we replace that hydrogen with CH3, and then we have to count 4. So this is 1, 2, 3, 4. So this one also has to be on the same side. So this would be, if this one is axial up, the methyls, since they're cis, have to be both up. So this becomes a CH3 here, and that's one's equatorial up. Now, the lowest energy conformation puts your substituents in equatorial positions. So the bigger the substituent is, the more likely it's going to be in the equatorial position. We call these sometimes locking groups, like the tert-butyl group is a locking position. 99.9% it's going to be in the equatorial position. Here we have an equatorial up and an axial up. So even if these flipped, which you need to be able to draw the flip. So if you flip this, and the flip is usually hard for people. So this methyl here has to be at the top, okay? And so this methyl here is going to have to be at the bottom. So then when you draw this, you draw, you flip it so you turn it inside out. This goes down. Okay, not the best ring, but now this methyl group is equatorial up, and now it becomes axial up. So when you flip a ring, anything equatorial becomes an axial, and axial becomes equatorial. But up stays up, and down stays down. So this other methyl here, so that's 1, or you could say that's 4. 4, 3, 2, 1. This is your 1 carbon. This would be axial up, so now it becomes equatorial up, and your hydrogen is down. Now notice this is equatorial up, and this is axial up. They both have to be up because they're cis. They're coming at you. But since this is axial and that's equatorial, neither one of them has any better energy than the other, so they're equally distributed between the equilibrium arrow. Okay, this one, we don't have to worry. This doesn't have a cis or trans, so no cis trans. So we'll go on to this one. This one here is trans. Okay, so it's a 1, 2, 1, 2, 3, 4, 5, 6. So this one is trans 1, 2 dimethyl cyclohexane. And our goal is to try to draw the chair conformation that gives it its lowest energy conformation. So we draw our chair. I think we can do better. So I am going to erase that. All right. Okay, so let's just put our little board here, and then we can draw. And then you can always erase this. This is what people do on their paper, and then they erase this. You know why we have erasers? People make mistakes. Alright, so there's that. And then you draw your axial up, axial down, axial up, axial down, axial up, axial down. And then you can draw your equatorial down, equatorial up, equatorial down, equatorial up, down, up. And then you're going to go and you're going to put this methyl here, and this methyl is up. So there's your CH3. Okay, and then we'll do this one, 2. So there's 2. And it is trans. So if this is axial up, this has to be equator, or this has to be down. So this has to be axial down. Now, your substituents are both in the axial position. So this is not going to be energetically favored. It's going to have a little equilibrium arrow, and your big equilibrium arrow will be in another energy conformation. So this is where we have to flip it. So this carbon here will go at the top, and this carbon here will go at the bottom. So when we flip this, we go down, up, down, up. Okay. And then you can always erase this if you want. All right. Those back in. Okay. So this one here is hydrogen up, hydrogen down, hydrogen up, hydrogen down, hydrogen up, hydrogen down, equatorial down, equatorial up, equatorial down, equatorial up, equatorial down, equatorial up. Now let's focus on this carbon here. The CH3, when you flip it, up stays up, but axial becomes equatorial. So this is equatorial up. And then this CH3 next door is down. And so it's axial down. So it becomes equatorial down. That's equatorial. And notice it's down. It's below the ring. And so with both substituents being in the equatorial position, this is going to be your lowest energy. Okay, let's try this one here. In fact, I will let you draw this one. This will be, so your POGIL activity for tomorrow will be to draw the lowest energy conformation. So I want you to name this compound, and then I want you to draw 2 energy conformations. So, because I want to see you do the ring flip, just like what we've been doing. And the other thing I want you to do, that's 1. The second thing I want you to do is to draw the lowest energy chair conformation for the following compound: trans 1-tert butyl 4-methyl cyclohexane. And I will tell you the tert butyl group is a locking group. So this tert butyl group, it has to be in the equatorial position. So those are your 2 POGIL activities for tomorrow.